Time for section 2.3, Biconditionals and Definitions. It's a pretty short section. In the last section, I had given you this example of a converse. I also said that it showed a situation where the statement was true, but the converse was false. I also said that the opposite would also sometimes happen like it does here. Here is the example I gave where the statement was false, but the converse was true. That definitely also happens a fair bit. However, for a biconditional, we want to deal with the situation where both the statement and the converse are true. So we would not be allowed to write a biconditional for the first couple of examples on the previous slides. But at this point, I need to note that this is one of those cases where mathematicians deal with a subject differently. In geometry, we only deal with biconditionals where both the statement and converse are true. That's why I wrote the golden rule at the top of the page. But I do need to point out here that in other branches of mathematics, they take a wider view and don't put that restriction on a biconditional. They write biconditionals when one or both the statement and converse are false. And they do a full workup on the truthfulness of the biconditional. In fact, in those situations, a false statement and a false converse make for a true biconditional. However, we aren't going to deal with that. In geometry, we place restrictions on the biconditional, and we will only deal in situations where both the statement and converse are true. I just felt compelled to tell you this in case you looked up biconditional and you're like, hey, wait, we can write them with false. What the heck's going on? I just wanted to make it clear that in geometry, we only deal with biconditionals where both the statement and converse are true. It makes for an easier time. So let's look at this statement, knowing that in geometry, we look for biconditionals with both a true statement and true converse. First, in case you didn't know, Halloween is on October 31st, the last day of October. Given that, this is a true statement. So we pass that check. Now we need to look at the biconditional. So I should probably write that down. Looking at the converse, it is also true. So now we have passed both checks. Both the statement and the converse are true, so we are allowed to write the biconditional. So what is the biconditional? Bi means two, and a biconditional takes two statements, one conditional and its converse, and combines them into one. You can also think of a biconditional as a conditional that works both ways. In any case, this is the structure of a biconditional. P if and only if Q. It no longer has the familiar if-then structure. Then doesn't even appear anywhere. So you start with P, the hypothesis of the statement. There is no if or anything else before it. And then you put the phrase, if and only if. And then you put the Q, the conclusion of the statement. In our example, it would look like this. You will need to get used to that phrase, if and only if. It signifies a statement as being universally true, working in every way. Also note that since a biconditional works both ways, you can actually flip it around. This works too, and is fine. Since a biconditional works in every way, it doesn't really matter which part comes first. Now let's work on some shorthand. Clearly, we wouldn't want to get hand cramps, so let's shorten that phrase if and only if. First, Paul Halmos, a Hungarian-born American mathematician, is generally credited with coming up with this shorthand for if and only if in the 1950s. Kind of looks weird, right? Looks like it would have been pronounced if. However, if you were to read that out loud, you would still say if and only if instead of if. It is only shorthand for writing it out, not pronouncing it. In any case, it is standard shorthand for if and only if, and you are free to use it if you like. However, it isn't the only shorthand. There is also this symbol. It also stands for if and only if. So this is another situation where you get to choose which one you like to use. All of them stand for the same thing. Finally, we get to the last bullet point, what makes a good definition? This is a minor topic, but biconditionals play a role in it, which is why it is presented here. In general, you rarely get asked to make your own definitions. Most of the time, you are given definitions that you are expected to use. For example, we have this definition of an obtuse angle from before. You are given this and you are expected to know it, but you didn't come up with it on your own. We aren't going to be expecting you to be coming up with a whole range of definitions. That said, let's look at what makes a good definition. First, a good definition uses terms that are commonly understood or have been previously defined. Now, I have already pointed out a few instances where textbook folks really stretch this idea of commonly understood. Far too often definitions, postulates, and the like are written in dense math speak, which is hard for normal people to understand. But in theory, if you really want to write a good definition, you write it so everyone understands it easily. The second quality of a good definition is that it's precise. It uses definite terms. It avoids vague words like large, almost, or kind of. In the definition of an obtuse angle on the previous slide, it was very precise in its description. Just saying, an obtuse angle is a big one, wouldn't have been very good. It went into specifics about just how big it had to be to count as obtuse. And lastly, there is this little quality that a good definition is reversible. In other words, you can write the definition as a true biconditional. And that's why this little definition tangent that we're on here is being presented now. This third quality of a good definition actually uses biconditionals. So for example, I can take my definition of an obtuse angle and write it as an if-then statement. The third quality says it should be reversible. So let's look at the converse. The statement is true. The converse is also true. Since both the statement and converse are true, we are allowed to write the biconditional. And there it is. Good definitions should work in every way. You should be able to write them as a biconditional. Here are some examples of bad definitions. Circles are shapes that have no corners. That's a true statement. But is that a good definition? A good definition is reversible. And here the reverse would be, shapes that have no corners are circles. And that's just not true. There are other shapes that have no corners. How about a point? How about an ellipse? A plane is an extremely large flat surface. That's true, but not nearly precise enough. Just how big are we talking? Even though I tripled up on the emphasis, bold, italics, and underlining, the trifecta, that still doesn't mean it clearly defines how big we are talking. It needs to be more precise. This one says, a fish is an animal that swims. That's true enough, but it needs to be reversible. We should be able to write it as a biconditional. But let's look at the converse. There are many animals that swim that aren't fish. Whales, humans, frogs, etc. From a geometry teacher's perspective, having you be able to write a good definition isn't that practical. You just aren't going to be doing it a lot. We're going to be giving you the definitions more often than not. However, it is a good way for you to practice your biconditionals and shows you biconditionals in action. So that's why we are showing you biconditionals here in that light.